Hamilton's broad and ample road, that ribbon of stars in the night sky, has recently been found to be our inside view of one of billions of galaxies in a possibly infinite universe.
Mythology and poetry, references to the Milky Way have always been pictures of light that runs like a river through the stars, was discovered by Galileo to actually be composed of stars itself, but stars too far and too faint to be resolved without a telescope. The Milky Way, which runs around our entire sky, was actually just our inside, edge-on view of the huge spiral collection of stars and gas and dust in which we reside, the Milky Way galaxy. The Romans called the circle of light the Milky Way, as we still do today, but we use the same name for our galaxy as a whole. And there are many other galaxies beyond our own, but the discovery of the Milky Way galaxy was the result of careful study of the distribution of the stars around us, the stars which are themselves part of the Milky Way galaxy.
When we look at the thousands of stars in the night sky, they seem at first to have a random distribution. But when those skies are clear and dark, most of the stars form a broad, hazy band that stretches from horizon to horizon. This grouping of stars is our own galaxy, the Milky Way. Photographs of other galaxies give us an idea of what we might look like from a distance of several million light years. Seen edge-on, the Milky Way would appear as a flattened system of stars with a central bulge. Around our system are many other stars that form a faint halo, so that a complete view of the Milky Way would look something like this illustration. This view of our galaxy and the fact that the galaxies in the universe, and not the universe itself, are very recent discoveries. Although the nature and origin of the universe has been standard speculation for philosophers, theologians, and artists for centuries, the first observational model of the Milky Way was developed by William Herschel in the late 18th century. After his discovery of Uranus, Herschel added to his continuous cataloging of globular star clusters and nebulae a count of the stars called star gauges. He would count the actual number of stars visible in the field of view of his telescope, and repeated this procedure in hundreds of selected areas throughout the sky. From the average of these counts, his star gauges, he developed this model of the Milky Way. Herschel's grindstone view was a stellar structure shaped like a flat disk, with the sun located very close to the center. The deep cleft to the right corresponds to the dark rift from Cygnus to Centaurus. Shortly thereafter, the third Earl of Rosse was making a detailed study of the nebulae and globular clusters cataloged by Herschel. Using a 1.8-meter reflecting telescope on his Irish estate, Rosse noted that some of the nebulae had a spiral pattern. Because the nebulae were more numerous along the plane of the Milky Way and not distributed evenly throughout the sky, Rosse concluded that they all must be part of our galaxy. The next comprehension was done by the Dutch astronomer Jacobus Kapteyn at the turn of this century. The most obvious problem with this theory was its inability to account for the distribution of globular clusters seen at the right. At the same time that Kapteyn was attempting a definitive analysis of the universe, Harlow Shapley was studying the globular clusters with the 1.5-meter Mount Wilson reflector in California. His studies eventually ended our sun-centered concept of the universe and did for our galaxy what Copernicus had done for the solar system. The globular star clusters that Shapley observed formed a roughly spherical system that was not centered on the Captian universe.
Shapley was interested in globular star clusters. Globular clusters are great systems of tens of thousands of individual stars, and they can be identified to very great depths in space. But moreover, it's possible to estimate distances to globular star clusters. Shapley set about, with a 60-inch telescope at Mount Wilson, finding the distances to more than 80 globular clusters that were then known. Now, he had their directions and distances, so this told him the three-dimensional distribution of them in space. And what he found was really remarkable. What he found was the sun did not appear in the middle of this distribution of globular clusters. They were spread roughly in a spherical way, but the sun way off to one side. So most of the clusters are over on one side of the sky.
Shapley successfully dynamically impossible. The stellar system, because of its mass, must be the center of the gravitational attraction that holds the clusters in their halo-like distribution. The Milky Way, as Shapley described it, looked similar to the grindstone model that Herschel had developed some 150 years earlier, but without the sun as the center. In order to center the galaxy on the globular clusters, the size of the Milky Way had to be greatly expanded.
Indeed, Shapley had the galaxy over 200,000 or 300,000 light years across. Today, the best guess is it's about 100,000 light years in diameter. We're at about 30,000 light years from the center. In 1920, the majority view in astronomy held that our galaxy, which was clearly a huge system, was the entire universe. And yet, from early times when telescopic observations first began, especially in the 17th and 18th centuries, many thousands of faint patches of light could be seen in space between the stars, little cloud-like things called nebulae. But the question is, what are these nebulae? Kant, Immanuel Kant, the German philosopher, in 1755, speculated that those things were island universes, as he called them, but he meant other galaxies like our own, far beyond the farthest stars of our system. William Herschel himself, who discovered many of these faint patches of light, thought for a time that he was discovering other universes. He once remarked to his sister Caroline, who helped him with his observing, thousands of universes. Late in his life, though, Herschel himself came to doubt that this was the case. Somehow, to him, they didn't look as though they could be systems of stars. And the debate really raged from that time until the middle 1920s. In fact, the most famous debate was between Shapley, who held that our galaxy was the whole universe, and he had good scientific reasons for it. There were some observations that seemed to be crucial that indicated that these nebulae could not be very far away. The observations, incidentally, have turned out to be wrong. On the other side of the debate, the Lick Observatory's Curtis, H.D. Curtis, had better insight in this case, although his arguments may not have seemed so sound, but he thought that those nebulae would turn out to be remote galaxies like our own.
The Shapley-Curtis debate was resolved in 1923 by Dr. Edwin Hubble using the newly completed 100-inch telescope at Mount Wilson, the largest telescope in the world at the time. Hubble was interested in solving the mysteries of Ross's spiral nebulae, the unknown hazy patches of light in the sky. He turned the large 100-inch telescope to the brightest of these objects and began to take photographs of it through the telescope. The patch of light was in the region of the sky called Andromeda. The 100-inch telescope was powerful enough to photograph the outer regions in some detail. Hubble was able to obtain photographs which resolved some of the outer regions into stars. When early photographs were compared to later photographs, it was discovered that some of these stars varied in brightness. Later studies showed that a few changed in brightness regularly. Studies of nearby regular variable stars had, in the past, shown that their periods of pulsation were uniquely related to their absolute brightness or candle power. Comparing the absolute brightness with the measurements of the apparent brightness then gave a measure of their distance. From a number of measurements of pulsating stars, Hubble found the distance to the object in Andromeda was 680,000 light years, proving that it was indeed another system of stars outside our own Milky Way. Within reach of the telescope were well over 100 million other systems, made up of billions of stars. They became known as galaxies. The essential factor that had eluded earlier astronomers was the measurement of the huge distances within the stellar system. Herschel, Kapteyn, and their colleagues had assumed that space, the interstellar region, was a true vacuum, optically transparent. Actually, space is pervaded by a thin haze of dust and gas, which dims and reddens starlight. Because earlier investigators could only see a short distance into this uniform interstellar smog, they placed our sun at its center. Consequently, their calculations about stellar distances and distribution were incorrect. They were caught in the middle of a rather immense optical illusion.
If you fail to allow for it, you come to the conclusion and that we're in the middle of it. It's only when you allow for the absorption by dust of stellar light on the way to us that you can understand the structure of our galaxy and its size. It does several things, most of which are basically a nuisance from the point of view of the stellar or galactic astronomer. Firstly, it cuts out the total amount of light you see. That's a nuisance. Secondly, it reddens the light, and that's a tremendous nuisance because it's generally the blue light that conveys the most information. And thirdly, it introduces into the spectrum of an object you happen to be interested in absorption lines and bands that have nothing whatever to do with the object but are merely caused by the interstellar gas and dust. There are lots of people who know what the dust is made of, but they know different things. I think it's probably fair to say that the majority view at the moment is that the average dust grain is a few microns in diameter and has a two-part composition, a core of heavy things like graphite and perhaps silicates like glass and rock bits, and a mantle around that core made up of frozen ices, frozen methane, frozen ammonia, water vapor, carbon dioxide, and that sort of thing.
The nature of these masses of the interstellar medium called nebulae was first analyzed by R.J. Trumpler of the Lick Observatory in 1930. The nebulae fall into two general categories, dust and gas. The dust nebulae are visible to us as silhouettes against a star-filled background, or as nebulae that reflect the light of nearby stars. The formation of this dust still interests astronomers.
It's got to be formed somehow because we see it. Some kinds of dust particles can be formed in the atmospheres of cool stars. And those dust particles whose cores are carbon are almost certainly the products of out in the atmospheres of cool stars. Carbon is quite refractory and quite happily turns from a gas to a solid at a temperature of a few thousand degrees. Some of the other particles must somehow have condensed in the vicinity of stellar explosions, supernovae, because they preserve in themselves the composition of the material that was made in the stellar explosion. But the details of how the dust condenses, I think, it's probably fair to say, are not clear at the moment.
The other general category of nebulae are the regions of interstellar gas, usually hydrogen, at a density of about 1 atom per cubic centimeter. Some of the hydrogen gases that are close to very hot stars become heated and glow with a primarily reddish light. These are called emission nebulae, or H2 regions, and are actually fluorescing in a manner similar to fluorescent lights. In addition to the hot glowing nebulae of hydrogen, there are enormous dark areas of cold neutral atomic hydrogen called H1 regions. The hydrogen doesn't give off energy that can be seen or photographed. However, these very small atoms rushing through the reaches of space sometimes collide. An electron in the hydrogen atom makes a magnetic flip with respect to the nucleus. During this process, the atom gains a small amount of energy. Eventually, the electron flips back, releasing the energy in the form of a photon whose wavelength is at 21 centimeters, or 1420 megahertz. Although this process may happen only once in 400 to 11 million years for an individual hydrogen atom, the vast number of high stream of 21 centimeter radiation that can be detected with radio telescopes. This interstellar dust and gas has been associated with the birth of stars.
It has long been felt, mainly on the basis of circumstantial evidence, that stars in fact form in large clouds of dust and gas which are known to exist in our galaxy. and then somewhat later in their evolution drift out into the open where we can see them. A lot of the evidence for this is, in fact, that we see very young stars, at least on an astronomical timescale. They have ages of a few 100,000 years, which have clearly fairly recently emerged from these dark clouds. A decade or so ago, when people were first able to begin making maps at infrared wavelengths, they did in fact find considerable numbers of cool sources embedded in these clouds, and there's been considerable debate as to whether these are protostars, i.e. regions of the cloud still collapsing to form a star, or whether they have in fact become very young stars which have developed their own gravitational energy sources and are now driving matter away from them again.
Once the interstellar regions of dust and gas were factored into the calculations of stellar brightness, the earlier distance errors were easily understandable. But the awesome distances in the universe were not apparent until the period luminosity relationship of variable stars was discovered. These stars vary in brightness. Their irregular random fluctuations render them fairly useless for calculating distance. But calculations can be made using the seemingly valueless stars whose brightness varies regularly or periodically. This star, for example, called an RR Lyrae star, changes its brightness regularly in periods of several hours year after year. Despite the fact that RR Lyrae stars are 10 times larger than our own sun, we regard them as small members of the family of regular variable stars. Searching through thousands of other stars, we find larger periodic variable stars called Cepheids that regularly vary in brightness in periods of days. Cepheids are roughly 100 times larger than our own sun. We also find the largest periodic variables in the sky, called Miras, which change in brightness regularly over periods of months. The cause of these changes in brightness is a physical pulsation, an alternate swelling and contraction in a rhythmic manner under the opposing forces of gravity and gas pressure, which are never quite in balance, as in a normal star like the sun. This pulsation occurs over and over again for many thousands of years. One of the most amazing properties of these regular variable stars is the beautifully simple relation between intrinsic brightness and period of pulsation. The larger, brighter stars have longer periods. By means of this period luminosity law, it is possible to determine the intrinsic brightness of a pulsating star and hence its distance from a simple knowledge of its period of pulsation. These measurements of period luminosity are done by using the telescope as a large camera, but instead of film, large glass photographic plates that don't stretch or curl are used. The plates are coated with very sensitive emulsions, specially designed for long exposures of faint light sources. Because the exposure times are long, the complicated shutter of a conventional camera can be replaced by a window shade in front of the lens of this telescope. The astronomer takes photographic plates of a selected region of the sky at intervals of a few hours, a week, a month, a year. At a later time, one of the plates taken tonight will be paired with one of the plates of the same region taken earlier. The two plates are placed in a machine that alternate. Upon careful examination, a comparison of plates taken a few hours apart reveals the stars with rapid light variations. A comparison of plates taken months apart reveals the slow variable stars. Measurements of the brightness of a given variable star on a series of photographs give a precise description of the way in which its brightness varies with time. This period luminosity relation was first discovered by Henrietta Leavitt while observing pulsating variable stars in the Magellanic Clouds. These clouds are actually among our nearest neighboring galaxies, only 180,000 light years away, but can only be observed from the southern hemisphere. The periods of pulsation of the variable stars range from a few days for the short RR Lyraes to over 100 for the Cepheids. There are also long period variables, called Miras, that only fluctuate in several hundred days. The RR Lyrae stars were Shapley's indicators clusters, which demonstrated the huge dimensions of our Milky Way. But Shapley insisted that his model of the Milky Way represented the entire universe, but he was hampered by the equipment available to him. Hubble, however, had access to the new 100-inch telescope at Mount Wilson.
Hubble obtained a plate with a 100-inch telescope at Mount Wilson of the Andromeda Nebula, as it was then called, Messier 31. He was looking for novae, new stars, because it was known by then that some of these nebulae occasionally contained stars that flare up in brightness, and he was hoping that they might give some hint to the distance. On that plate he took in October of 1923, he found that what appeared to be a nova really was a variable star. Compared that plate with others taken previously and found that the star was varying in light in a characteristic way. He recognized that it was a Cepheid variable. Now, Cepheid variables are well known in our galaxy. They are giant stars, hundreds of times as bright as the sun, or sometimes thousands of times as bright. In the Andromeda Nebula, that Cepheid variable found by Hubble was exceedingly faint, which showed that the nebula must be extremely far away to account for that faintness. Hubble presented this material after he had a chance to confirm it by finding many other Cepheid variables in the Andromeda galaxy.
These variable stars, the Cepheids, are discovered in 1784 by John Goodricke. Their regular period luminosity relation is the key to their usefulness. In the late 1940s, a newer 200-inch telescope was dedicated at Palomar Mountain. This telescope was the first to allow the observer to ride on the moving telescope at the upper end of the tube. Light from a galaxy is reflected from the large 200-inch mirror to the prime focus cage. The astronomer makes only a cursory visual sighting, enough to compose the object on the photographic plate. The tremendous collecting powers of the 200-inch telescope, the very long exposure times, and the sensitive photographic emulsions have made possible the discovery of variable stars in the galaxies. As a result of these studies, Hubble's original distance scales have had to be revised upward. The distance to the great galaxy in Andromeda has been revised from 680,000 light years to a distance of over 2 million light years. The distances of more remote galaxies have been revised upwards of 4 to 7 times. Attention now turned to the search for an accurate description of the nature and size of the Milky Way. At the same time that Hubble was examining Andromeda, Lindblad showed that a puzzling phenomenon of stellar motion called asymmetrical drift could be precisely explained if our own galaxy were rotating.
These by their mutual gravitation. And our galaxy is rotating like a great wheel. And just as the planets revolve around the sun, so the stars of the galaxy revolve about its center. The sun, at a distance of approximately 30,000 light years from the center, takes 200 million years to revolve once about. Now, we know how far away the sun is from the center, so we know the size of its orbit. We know how long it takes the sun to go around. This gives us a very simple way of calculating how much matter there must be in the galaxy to account for the sun's motion. We can use Kepler's third law, just as we find the masses of planets in the solar system from their satellites. We find that the galaxy contains enough mass to account for something like 100 billion suns. Since typical stars are a little less massive than the sun's a little better than average, we would estimate that there may be the order of 400 billion stars, or 400,000 million stars in our own galaxy.
As majestic as the Milky Way is, with its hundreds of billions of stars, astronomers like Hubble discovered that it was just one of billions of other galaxies, no less impressive than our own. The cosmos is awesomely vast, and we are very small.